This is Project 5, video number 3, the one where we do final touches. One thing I left out before was I was doing some printouts just for testing purposes. Better get rid of those. Let's see what this function does. And I think you got an idea what it does. I'm going to go ahead and pause the video so you don't have to watch me type all this in, but just got to describe it from what they said in the handout. Okay, so I got the description of what plot F versus T does, and then the input variables, and I should probably mention output variables. Just to make sure people realize it doesn't return anything. Output variables, plot F VT, what did I call it? F versus T. He returns nothing. And then percent by Jeffrey Schnick. And then attribution. Okay, let's see if we need okay, this will be our time step. So I go percent time and step. Might see if there's any code that's not clear. Let's try describing this a little bit. For each time starting at time 0, the instant the spring first makes contact with car 1, the one that's up front, we calculate for each time in steps of delta t the position, velocity, acceleration, and force of spring on the assumption that the velocity and acceleration are constant in the approximation. During the time interval delta t. We stop, when the spring, I think my stopping condition was the length of the spring, but let's make sure. So while x is equal to 0, so then the spring compression is reduced to just below 0. Alright. So that more or less explains that part of the code. And here next 2 lines we set the lower limit of the force to 0. Axis of the graph to 0, while letting by the values in the array F. Alright. I think that might do it. Let's save it. Try running it. So I gotta get into the right directory. ps131 projects, project 5, my code, and I should be able to run that now. So move this back over here so you can see better. Plot F versus T of, and then I had something like 2, I think I'll go with 2 meters per second to start with, and I wanted a K in the ballpark of the gravitational force acting on the car, which would be it was 1,000 kilograms, so we're talking 10,000. That would be newtons per meter, and we'll call it 10,000 newtons per 10 centimeters, so it's not compressing too much. So let's take a look and see what we got. Alright, still working. I gotta title the axes, title the graph. So let's work on that. Title. Spring force magnitude. Better spell title correctly. Versus time. And then, is it X label, I think? Time in seconds. That should be in square brackets, not parentheses. And then Y label. I just got force to keep it simple, but it's really the magnitude of the force exerted by the spring, and that'll be in newtons. And quote, and parentheses, semicolon, Control S. Try running it. Spring force magnitude versus time. Force, time. Alright, I think that's looking pretty good. Let's look at the checklist, see if I got everything covered for the entire project. Automobile manufacturer wants information, I guess. 2 cars, each car that. Okay. Takes us to this argument, the value of the speed of the car 2 in meters per second, and the force constant. So V2 0 and the force constant, good there. And then magnitude of the force exerted on the front car, that's cool. While loop come in handy. Let's take a look at yeah, bumps into car 1, so I got car 1 in the front. That's cool. I did use a while loop. Alright, continue checking. Pencil and paper, algebraic solution to the problem, outline of the steps. I definitely did that. Okay, pencil and paper part, I definitely had an algebraic solution, an outline of the steps, to the extent that an algebraic solution was possible. So I gave the things that I would be calculating in there. For the programming part, I think I made a reasonable attempt. I guess it's got to work properly. Make sure it prints nothing to the command window. I want to check that again because, yeah, okay, I've run it twice there and it's not printing anything. Run it again. Okay, because I did have something in there for a while to test it out. And then, what else do I need to do? Print nothing to the command window. 1 point for documentation. Graph must be titled, axes labeled, what's being plotted, and the units. So, let's make sure I got it's titled Spring Force Magnitude versus Time. I could call that the Spring Force on car 1, but I think we're good there. Force versus Time, units. I think we're in good shape there. And then, what else do I need? Have your name in it. I remember writing my name, make sure that didn't get wiped out. So, by Jeffrey Schnick, that's cool. And then your code must be documented. For each function, this will include a comment stating what the function does. Okay, I got that big one up front saying what it does. Here's where it says what it does. And then I think I got to address the variables. Say what it does. If it takes arguments, comments stating what each argument is, got that covered. In the case of a function that returns one, doesn't return anything. For the case of a function that includes segments that are not self-explanatory, I think anybody reading this code deserved a little bit of an explanation on what's going on with this big while loop. So up here I'm just setting things up for the while loop. X1 minus L0. I think that is pretty self-explanatory. The position of car 1 minus the unstretched length of the spring. It's kind of cool that we never have to worry about what the unstretched length of the spring really is. And then what else do we have? that x2 is equal to 0 is telling me what the origin of my coordinate system is. So I think I've explained well enough the stuff that might not be clear. And then provide attribution. So I didn't have to look up anything when I was doing this one. So I got my attribution line on there. I guess I want to make a quick check on whether or not this thing is making sense. So and I'm going to get my calculator out for this. The impulse delivered to the front car, for instance, should be the same no matter what, because in the end you apply conservation of momentum and conservation of energy after it's lost contact with the spring. The velocity shouldn't determine what the spring constant was. So the impulse delivered to the front car has got to be the same for any spring constant. Now the velocity would affect it, but for any spring constant I should get the same result. And I'm going to approximate this as a triangle. There's a right triangle there, and then another one that's identical to the right of it. So imagine a straight line down here. And it's got a height that's roughly the maximum there, which is 15,000 newtons, and a time that looks like it's about 0.115, I'll call it. Go ahead and multiply those numbers together. 0.115 times roughly, I think it's 14, I'll call it 14,500. And I get 1667, and then I want to go back to the main MATLAB window and run that again, but with a very different spring constant. So this one wouldn't be reasonable for a car, but interesting, it takes quite a bit longer. Well, that makes sense, it should be in contact longer if it's got a weaker spring, but that'd be a big, long, weak spring, so not very realistic. But here we've got, I call that 1,450, and then times 2.2. So I'm not getting the same. No, I'm okay. I think I just made a mistake in making the check. We're at about 1.15 times 1450, which gives us the same value, 1667.5 Newton seconds of impulse, just as before. So it does look like the impulse is right. There could be a caution if somebody uses too stiff a spring, so that the whole contact time is very, very small. It might have to make this smaller for accuracy. So the user might have to make this smaller for precision in the case of a spring constant in excess of 100,000 newtons per meter. So I want the text wrap on that. And we'll just leave it like that. So there's the time step, but it is working. So the impulse is the same in both the case of the strong spring and the weak spring, and so I'm going to call this a wrap for video 3 of project number 5.